Hello everyone, welcome to Neso Academy. In the previous lecture, we have implemented all 7 logic gates in Vivado using VHDL. And now, we are implementing our first combinational circuit, that is, the half adder. And in the 5th chapter, different modeling styles in VHDL, I have already explained all 3 modeling styles: behavioral modeling, structural modeling, and data flow modeling with the help of the half adder theoretically. And today we will implement the half adder using behavioral modeling practically in Vivado. So, our today's topic is half adder using behavioral modeling in Vivado with the help of VHDL. Now, before implementing the half adder in Vivado, let us quickly revise what is the half adder. Now, half adder is an adder that adds 2 single bit inputs and generates 2 outputs, sum and carry. But why we are calling this half adder as half adder? Because it performs half of the work required for full binary addition. A complete binary addition adds 2 single bit inputs along with the input carry from the previous stage. But the half adder only adds 2 single bit inputs and not any carry input from the previous stage. So I hope you understand why we are calling this half adder as half adder. Now let's see its formal definition. Half adder is a combinational circuit that adds 2 single bit binary inputs. Now half adder is a combinational circuit. What is combinational circuit? Combinational circuits are the circuits whose outputs entirely depends on present input values. So our half adder is a combinational circuit. How? Half adder generates sum and carry, and this sum and carry entirely depends on the present 2 single bit binary inputs that we are adding. Therefore, a half adder is a combinational circuit. Second point, half adder generates 2 outputs, sum and carry. As I already explained, half adder adds 2 single bit binary inputs and generate 2 outputs, sum and carry. Now let us understand this half adder using truth table. So this is the truth table for the half adder. Here we are adding 2 single bit binary inputs A and B, and it is generating 2 outputs, sum and carry. For 2 inputs, we are having 4 input combinations 0 0, 0 1, 1 0 and 1 1. Now, when both inputs A and B are equal to 0, which means 0 plus 0. Now 0 plus 0 will give sum as 0 and carry as 0. When A is 0 and B is 1, so 0 plus 1 will give sum as 1 and carry as 0. When A is 1 and B is 0, which means again we are adding 1 with 0. So sum will be 1 and carry will be 0. In the last combination, when both inputs A and B are equal to 1, so here we are adding 1 with 1. Now 1 plus 1 will give sum as 0 and carry as 1. So I hope you understand this truth table. Now, in order to generate the logic diagram, we need to find the Boolean expressions for sum and carry. For sum, look at these 2 input combinations when sum is equal to 1. When A is 0, B is 1, and when A is 1 and B is 0. Now here we can see A0 means A complement, B1 means B. So, sum is equal to A complement and B or A and B complement. So, Boolean expression for sum will be A complement and B, or A and B complement, which is equal to A XOR B. So, Boolean expression for sum is A XOR B. Now, let's find the Boolean expression for the carry output. Now, here we can see carry is 1 for last combination only, when both inputs A and B are equal to 1, which means carry is equal to A and B. Now, using these two Boolean expressions, we can construct the logic diagram. So, this is the logic diagram for the half adder. Here we can clearly see sum is equal to A XOR B and carry is equal to A and B. We are using only two logic gates to represent this half adder. Now, let's implement this half adder in Vivado using behavioral modeling. Now, I hope you remember what is behavioral modeling. In behavioral modeling, we describe what the circuit does and not any internal logic using the sequential statements. For example, if-else statements and case statements. So, today we will implement this half adder using behavioral modeling with the help of if-else statements in Vivado. So, let's implement our half adder in Vivado using behavioral modeling. So, we are in Vivado and this is our VHDL code editor. And here I have written the behavioral modeling code for the half adder. Now, the code starts with IEEE library along with the standard logic package from the IEEE library. Now, after library declaration, we are having our entity block, starting with the keyword entity, and here I have named this entity as half underscore adder because we are writing the VHDL code for the half adder. Is port. Now inside this entity, we will declare our input and output ports. Now the half adder has 4 ports. 2 are input ports and 2 are output ports. Here I have declared A and B, the two numbers that we want to add as input ports, and the two remaining signals, sum and carry, as output ports, and all of them as standard logic data type. After port declaration, we can end this entity using the keyword end with the name of the entity half adder. After entity declaration, we are having our architecture block, starting with the keyword architecture, and here I have named this architecture as behavioral because we are writing the behavioral style VHDL code for the half adder of the entity name half adder is. Now let's begin our architecture, starting with the process block with sensitivity list. I have already explained that we write behavioral modeling code inside the process block only using sequential statements. So, process with sensitivity list, which includes input ports A and B, meaning whenever these two inputs A and B changes, the entire code inside this process block will execute from the start to the end. Now, let's see what is written inside this process block. Inside the process, we will start our code with the keyword begin with the if-else statements for the behavioral modeling code. Now, we can implement the truth table of the half adder using 3 conditions only, because in the truth table, the second combination and the third combination, when A is 0 and B is 1, and when A is 1, B is 0, both combinations generate same results, sum as 1 and carry as 0. Therefore, we can implement the entire truth table of the half adder using 3 conditions. Let's see them. The first condition, if A is equal to 1 and B is equal to 1, then assign sum as 0 and carry as 1. Now, this is our fourth combination of the truth table. When both A and B are equal to 1, then sum will be 0 and carry will be 1. If not, then move to the next condition. Else if A is equal to 0 and B is equal to 0, then assign sum as 0 and carry as 0. Now this is our first combination of the truth table. When both A and B are equal to 0, then the output sum will be 0 and the carry will be 0. If not, then move to the next combination. Else sum as 1 and carry as 0. When A is 0 and B is 1, and when A is 1 and B is 0, then sum will be 1 and carry will be 0. The remaining two combinations with the help of one condition. Now we can end this if-else-if statement using the keyword and if, and we can end this process using the keyword and process. Similarly, we can end this architecture using the keyword and with the name of the architecture, behavioral. So, I hope you understand these if-else-if statements using behavioral modeling code. Now, let's see the schematic diagram generated by Vivado for this half adder. For that, go to RTL analysis, click on Open Elaborated Design and select Schematic. Now, this is our schematic diagram generated by Vivado for the behavioral modeling code of the half adder. Here we are having the two numbers A and B that we want to add. And here we are having the outputs sum and carry. Now, let us verify this schematic diagram. Now, here we can clearly see this AND gate, where inputs are A and B. So, this AND gate is generating A and B, which is directly connected with the output carry. So, here carry is equal to A and B, which is absolutely correct. Now, let's verify the schematic diagram for few combinations, starting with the last combination when both A and B are equal to 1. So, when A is equal to 1 and B is equal to 1, then this AND gate will generate the output as 1. Therefore, the final output carry will be 1, which is correct. Now, focus on this multiplexer. The select line of this multiplexer is directly connected with the output of this AND gate, which means here select line is equal to 1. Now, multiplexers generated by Vivado are little different than what we have studied in digital electronics. In 2x1 multiplexer, we know that when select line S is equal to 0, then input I0 is selected as output, and when select line S is equal to 1, then input I1 is selected as output. But in Vivado, when select line S is equal to 1, then input line I0 is selected as output, and when select line S is equal to 0, then input line I1 is connected as output. And the same thing is written over here. On input line I0, we can clearly see S is equal to 1, B1, which means select input line I0 when S is equal to 1, which is of size B1. B1 means bit 1, the size of select line, which is of 1 bit. So, when select line is equal to 1, then select input I0. Now here, we have S is equal to 1, which means input I0 will be connected to the output. And here we can see input I0 is directly connected with the ground, which means input I0 is equal to 0. Therefore, the output will be 0 and hence sum will be 0. So, when A and B both are 1, sum is 0, which is correct. Now, let's verify another combination when A is equal to 0 and B is equal to 1. So, when A is equal to 0 and B is equal to 1, then this AND gate will generate the output as 0, which is connected with this carry. So, here carry is equal to 0 when A is 0 and B is 1, which is correct. Now for this multiplexer, the select line is equal to 0. When select line is equal to 0, then the input line I1 will be connected to the output. Now remember this part. Let's understand the remaining schematic diagram. Here we can clearly see the both inputs A and B are directly connected with these two blocks named as RTL underscore EQ. RTL underscore EQ means register transfer level equal blocks. Now these blocks are comparing their respective inputs. If they are equal, then their output will be 1. If they are not equal, then their output will be 0. Now focus on these two blocks. Here we can clearly see that the input I1 for the first block and the input I1 for the second block are directly connected with this ground, which is equal to 0. So input I1 in both of these blocks are equal to 0. Now this first block is comparing input A, which is equal to 0, with this I1, which is also equal to 0, which means 0 is equal to 0. Therefore, this RTL EQ block will generate the output as 1. Now for this second block, RTL EQ block is comparing the input B, which is equal to 1, with the input I1, which is equal to 0. So here we can clearly see 1 is not equal to 0. Therefore, its output will be 0. So the output of the first RTL EQ block is 1 and the output of the second RTL EQ block is equal to 0. Now these two outputs are acting as the inputs for this AND gate. Therefore, 1 and 0 will give output as 0. And this output is acting as the select line for this multiplexer. So here, select line is equal to 0, which means input I1 will be connected to the output. And here we can clearly see input I1 is directly connected to this high voltage, which means input I1 is equal to 1. Therefore, the output of the first multiplexer will be 1. And this output is directly connected to the input I1 of the second multiplexer. And I hope you remember that here select line S is equal to 0, which means input I1 will be connected to the output sum. And here input I1 is equal to 1, which means sum will be 1. So when A is equal to 0 and B is equal to 1, then we are getting sum as 1 and carry as 0, which is correct. And I hope you understand this schematic diagram. Similarly, you can verify the remaining two combinations as well using the same schematic. Now, let's see the simulation waveforms generated by Vivado for the VHDL code of the half adder. For that, go to Simulation, click on Run Simulation and select Run Behavioral Simulation. It will take some time, just wait for a few seconds. So, this is our simulation waveform window, and here we are having our two inputs A and B and two outputs sum and carry. Let us quickly assign both inputs A and B as equal to 1 to verify our VHDL code. For that, right-click on signal A, select force constant and change the value radix as binary because we want a binary number. Then assign a force value 1. Then click on OK. Similarly, we can assign 1 for the input B. For that, right-click on signal B, select force constant, change the value radix as binary and assign a force value 1. Then click on OK. Now let's verify our results. For that, let me run this simulation for 100 nanoseconds. For that, click on Run for 100 nanoseconds. Now our waveform is generated. Let me maximize this. Let me zoom in further. Now here we can see when A is equal to 1, we can clearly see in the waveform as well and when b is equal to 1, then we are getting sum as 0 and carry as 1, which is absolutely correct. Similarly, you can verify other 3 remaining combinations as well. So, I hope you understand the practical implementation of the half adder in Vivado using behavioral modeling. So, I hope you understand the implementation of half adder using behavioral modeling in Vivado. And in the next lecture, we will implement it using structural modeling, which is very important. So, we are done with the topic of half adder using behavioral modeling. With that, we are done with this lecture. I will see you in the next one. Thank you.